So, for example, let's say that we have a normal vector of a plane given by the vector, let's say 1, 4, negative 2. And let's say that we have a point on this plane given by 0, 5, 3. So using this normal vector and a point, I want to come up with an equation for the plane. And given what we had just done before, we know that our vector equation for a plane, our normal vector, dotted with the difference between any old point and our position point, has to be 0. So first, I'm going to look at my x minus x naught. X naught in this case is 0. Y minus y naught in this case is 5. And z minus z naught in this case is 3. This is the difference between the initial point and my point xyz. And I know that this vector dotted with the normal vector, which in this case our normal vector is 1, 4, negative 2, had better be equal to 0. Because that means that my point xyz must be on the plane. Computing this out, I can go ahead and perform the dot product if I want to, and it'll simplify the equation. And I see that when I take the dot product of x minus x naught dotted with 1, that's going to be 1 times x minus 0, which in this case is just x. The next product that I look at is y minus 5 all multiplied by 4. So I get plus 4y minus 20. And then my final component of the dot product is going to be z minus 3 times negative 2, which gives me negative 2z plus 6, which equals 0. And I can simplify this one more step by having my negative 20 plus 6 is negative 14. And if I add negative 14 to both sides, I end up with x plus 4y minus 2z equals 14. So here is an equation for a plane with normal vector 1, 4, negative 2 and point 0, 5, 3. Let's go ahead and check. And by check, I mean I'm going to see, is the point 0, 5, 3 actually on this plane? On this plane. Well, let's go ahead and plug it in and see what happens. So if x is equal to 0, I get 0. If y is equal to 5, I get 20. And if z is equal to 3, I get negative 6. And lo and behold, 20 minus 6 is exactly equal to 14, which is exactly what we wanted. Meaning that this particular point satisfies this equation, which means that this point must live on that plane. Another thing that I want to make note of is the fact that let's compare the equation here that we had with our initial normal vector. Notice the coefficient on our x is equal to 1. The coefficient on our y is equal to 4. And the coefficient on our z is equal to negative 2. This isn't a coincidence. If you look back through the algebra, if I'm given an equation of a plane in this form, I'll always be able to look back and see what my normal vector was by reading off the coefficients of each of those terms. We'll see this in greater detail when we talk about gradients later on in the term. So the final skill that we want to talk about is using 3 points to define a plane. So let's say that we have 3 points. Let's say our point A is equal to 1, 3, 2. Let's say our point B is equal to negative 1, 4, negative 1. And let's say our point C is equal to 5, negative 2, 0. So I have 3 points in space. It makes sense that 2 points wouldn't be quite enough to define a plane. That could give me a line, but there are a lot of different planes that go through that line. As soon as I fix that third point, it's like a three-legged chair, that'll always give me exactly a plane. But this isn't written in terms of our normal vector and our position vector, so we're going to have to do a little work. So we know that we could use any of these points to be the point for our initial position vector on our plane. But how do you come up with the normal vector? Well, let's draw a picture to start. Instead of doing an accurate picture, I'm going to do a heuristic picture, meaning that I'm going to represent my points A, B, and C sort of haphazardly without actually associating it with where they are in 3 space. A, B, and C are points, and I actually want to come up with vectors. Because if I think of creating vectors, a vector from A to B and a vector from B to C, these are going to be vectors that live on the surface of my plane. And once I have 2 vectors that live on the surface of the plane, I could use those vectors to give me a normal vector. That's something that we talked about last time. Given 2 vectors, we know that if we take the cross product of those 2 vectors, it'll always give us a normal vector, a vector that's orthogonal to those original 2 vectors. So let's do that. Our first step, let's come up with vectors, the vector that goes from A to B and the vector that goes from A to C. So how do we do that? I'm going to take A minus B, actually points in the other direction. So I'm going to take the vector starting at the point 1, 3, 2. I need to end up at the point negative 1, 4, 1. So my first vector, my vector AB, is going to be the vector negative 2, 1, negative 1. And that's taking negative 1, minus 1, 4, minus 3, 1, minus 2. And then on my next vector, my vector, I guess maybe I should write this as the vector CA, because it's actually, no, it's AC, because it's starting at A and moving to C. Either way, it would be the negative of it. And C is my point 5, negative 2, 0. So to get this vector, I know that I'm going to take 5 minus 1 is 4, negative, whoops, 5 minus 1 is 4, negative 2 minus negative 5 is 3, and 0 minus negative 2 is 0. So now I have 2 different vectors, and I know that these vectors live on the surface of the plane. So that's my step 1. Step 2 is to find the normal vector. And in this case, our normal vector is going to be the cross product of these 2 vectors that we found before. So I'm going to find the cross product of negative 2, 1, negative 1, crossed with 4, negative 5, 2. Now, what happens if I were to cross them in the opposite order? As we know from our right-hand rule, it means that instead of having a normal vector pointing this way, we'd had a normal vector pointing that way. And you know what? It really doesn't matter which direction our normal vector is pointing. So to take this cross product, I'm going to find the determinant of the 3 by 3 matrix with I, j, and k along the top, with negative 2, 1, negative 1 along the second row, and then 4, negative 5, negative 2 along the third row. So when I take the determinant, it's the coefficient I times the determinant of this smaller 2 by 2 matrix, which is going to be 1 times negative 2, which is negative 2, minus negative 1 times negative 5 is positive 5, minus the j times the determinant of this 2 by 2 matrix, omitting the jth column, and I get negative 2 times negative 2 is 4, minus negative 1 times 4 is -4, plus our final component k is the kth component is going to be the determinant of this 2 by 2 matrix, which is -2 times -5, which is +10, minus 1 times 4, which is 4. Let's simplify our arithmetic, and we see that the ith component of our vector is going to be -7. The jth component is going to be negative of 4 minus 4, wait, 4 minus -4 is positive 8, so I end up with -8j, and I have 10 minus 4, which is 6k, which means that this final vector is going to be given by -7, -8, 6. What vector is this? Well, the whole reason why we did this was to create a normal vector. So this is our normal vector n. And we're done. We're going to use A as our initial point, or our initial vector, because that's the vector, or that's the point that emanated the other two vectors. And we're going to use this as our normal vector. So our final equation is going to be our A written as a vector, which is going to be x minus 1, comma, y minus 3, comma, z minus 2, dotted with our normal vector, -7, comma, -8, comma, 6. And we know that this dot product has to be 0 in order for this x, y, and z point to live on our plane. This is our vector form, and if we wanted to, we could multiply out our vector form to be able to come up with the scalar form, just like we saw before. Our scalar form being the -7 times this, the -8 times this, and the 6 times that. Thanks so much. That's all we want to talk about in this section.